So, in the beginning lecture, in the first in the introductory lecture, so let me briefly touch upon signals and systems, some basic sequences, some of the details that we deal with when we I would say we would deal with signals and systems. So, let us try to get a hold of what basic signals are, what basic systems are, and how we apply these ideas towards the rest of the course. Okay. So, I would start with 1D signals and systems. So, let us start with basic sequences. Now, one of the basic sequence one can think about is the delta sequence, which is 1 when n equals 0, which is 0 otherwise. Then we have the unit step, which is 1 for n greater than or equal to 0 and 0 else, and we can think about other sequences such as exponential sequences, and if say x of n is a power n u of n, where u of n is this unit step sequence, and if modulus of a is less than 1, it is an exponentially decaying sequence. You may encounter many sequences. Now, from systems perspective, there is a differentiation between what a sequence is and what a system is. A sequence goes through a system. A system is basically, you can think about it as having an input sequence and it produces an output sequence, right. So, if you can think about it in this form, x of n is some input sequence, it goes through some system T and it produces this output y of n, and the system T is an instance of a system. T is an instance of a system. There are many systems. The simplest system is the delay system. So, if I take an input x of n and I delay by k units, right, I get x of n minus k, and that is a delay sequence. So, how can you realize a delay system? By just taking a signal and pass this through a tap delay line, right. I mean, you pass this through a tap delay line and you can realize a delay of k units. We can have a moving average system. And what is this moving average system? This can be described by this equation. The output is basically a moving average of the input over a window of m1 plus m2 plus 1 units, right. There is something in the past, there is something in the future, and I just take an average and I basically get a moving average, a running average. Systems could be memoryless or they could have memory. So, what does this mean? Say if the output y of n depends only on the input x of n, then it is a memoryless system, because it is only depending upon the current sample and nothing in the past. A good example is y of n is x cube n or y of n is some x square n plus 2x of n and so on, right, because the output y of n is depending only on some function of x of n. Now, if say y of n, this is memoryless, and if say y of n is some x cube of n plus some x square of n minus 1 plus some x of n minus 2, say suppose, then we can think about this as a system having memory, because you are requiring some inputs from the past, that is at time step n minus 1, at time step n minus 2, and so on and so forth. So, there is this notion of linear versus non-linear systems, and this is something really important in signal processing. So, all linear systems abide by something called the superposition principle. And this superposition principle has two components, one is additivity and the other is scaling or homogeneity. So, we will see what these properties are. So, let us say the system T is acting upon inputs x1 of n and x2 of n, and it gives you some y1 and y2, where y1 of n is the response of the system to x1 of n and y2 of n is the response of the system to the input x1 of n. So, y1 corresponds to x1 of n and y2 corresponds to x2 of n, and this if this relationship is satisfied, T of x1 plus x2 is T of x1 plus T of x2, then we call this as additivity, or it satisfies the additivity property. And T of some scaled version of the input, if it gives us a scale of the response of the system to the input, then it is called the scaling property or homogeneity, right. Now, if we invoke properties P1 and P2, we can say that T of A1 x1 of n plus A2 x2 of n is A1, the response of the system to x1 of n, plus A2 times the response of the system to the input x2 of n, and this is the superposition rule or the superposition property. And you will see this in electrical circuits when you have to look at elements such as resistors, capacitors and inductors, and these are essentially linear circuits. And if you bring in diodes, transistors, MOSFETs and other circuit elements, it is basically non-linear system, and you can see a non-linear system does not satisfy the superposition principle. And there is something called time invariance when we bring this into systems understanding, right. What is this notion of time invariance? Suppose an input sequence suppose an input sequence x of n is delayed by n naught, and let us assume that the sequence is x1 of n, which is x of n minus n naught. If the output sequence y of n is also delayed by n naught, that is y1 of n is y of n minus n naught, and x of n corresponds to y of n, and if you delay x of n by x of n minus n naught, my output is also delayed to y of n minus n naught, and if this property holds, then it is called shift invariance. Now, you might want to ponder about if I give you a sequence y of n which is x of some L times n, where L is any integer, I would say positive integer, is this shift invariant? I mean, whatever I did just now, I mean, I said y of n is x of L times n, and this is basically, this process is called decimation, and we will deal with this extensively in the multi-rate signal processing module. So, I want you to examine if this decimation process is shift invariant. Another concept which is important is causality. A system is causal if for every choice of n naught the output sequence at time n equals n naught depends only on the input sequence for n less than or equal to n naught. That means, a system is causal if for every choice of n naught the output sequence at time n equals n naught depends only on the input sequence for n less than or equal to n naught. That means, if I have all the past inputs then and the current input, then I can specify my output sequence. That means, this is the notion of causality. If I am anticipating something, then it is anti-causal. So, let us see some examples. Y of n is x of n plus 1 minus x of n. This is anti-causal. Why? Because the output at time n depends upon the input at time n, no doubt, and also the input at time n plus 1, that is some sample in the future. So, this is a sort of a very powerful idea, because something now is depending upon some input in the future, right, and that is anti-causality. and if y of n is say of this form x of n minus x of n minus 1, this is causal. Causality is a powerful idea, and one has to think if the universe is causal because this is depending upon the time reference, and the moment you remove the time reference, then you lose this notion of causality, right. If you lose the notion of time and everything is just in space, right, it is just there is no notion of this causality. I mean, there is everything seems to be the same, there is no notion of phase or no reference to time, and this is a very important concept. And sometimes you may encounter anti-causal systems, and you could make them causal by by delays and delaying things. For example, if I put a unit delay on the system that I described here, right, x of n plus 1 minus x of n. So, with a unit delay x of n plus 1 would give me x of n, and with a unit delay x of n would give me x of n minus 1. So, I can convert an anti-causal sequence to a causal sequence by introducing delays, and you will see how this could be useful particularly when you are building systems. Now, another notion in this study, another notion in the study of systems, or a concept, another concept in the study of systems is stability, and we will discuss what stability is. A system is bounded input, bounded output. Bounded input, bounded output. A system is bounded input, bounded output, stable if and only if every bounded input sequence produces a bounded output sequence. So, what does this mean? So, if every bounded input sequence produces a bounded output sequence, then it is called Bibo stable. Now, in precise language of mathematics, what do we mean by bounded input? Input is bounded if mod x of n is less than or equal to some quantity b suffix x, which is strictly less than infinity for every n, and Bibo stability requires that the output of the system to the input x of n, which is y of n, that is bounded. That means there exists some b suffix y which is strictly less than infinity, such that the magnitude of y of n is strictly less than or equal to this b's of y for every n. Now, some things that you want to ponder about is, suppose I give you y of n to be the summation of the unit step from the past, that is from minus infinity to the time step n, right, and we can say that this is a 0 when n less than 0 and it is n plus 1, because you have to count u of 0 and there are n such time units. So, this is going to be n plus 1 for time n greater than or equal to 0. Now, is this bounded? Probably not, it is not. Why? Because as n goes to infinity, because this holds for all n, right, and n could be also infinity. So, when n goes to infinity, y of n heads to infinity. So, therefore, it is not bounded. So, this is an example of a unbounded system.